So this time we will discuss about the finite square well. The finite square well. So first let me define what is finite square well. So from the name you can guess that the potential is finite somewhere. So it is minus V0, as I am calling it well, so it is minus V0. It is for minus AX and 0 for other region, that is A. So first we will find out the wave function for the region x mod x greater than A, precisely for x less than minus A. Okay, so here you can see potential is 0. So Schrödinger equation becomes b square psi dx square equals to t psi. So you can write this in this way. So where k equals to, you know, it is h bar, right? So the solution, general solution, you are well familiar with, minus kx, because it is plus, so it is exponential k plus exponential kx. Okay, so now if I consider x equals to, because it is less than minus it, if I consider if x equals to minus infinity, if I put this, so generally you can see that here a term will blow up. So we are left with only b part. Fine. So it is actually for x to minus a. So here let me draw the potential well actually for your convenience. So sorry, it should be symmetric. Okay. So a, this should be also a. Okay. So this is actually minus v0. Okay. So this is the potential actually. So now I will, so first we have calculated for this part, and now we will derive psi for this middle part. So for x a, so here vx equals to v0 minus v0. So Schrödinger equation becomes minus v0 psi equals to e psi. Okay. So you can rewrite the equation in this way easily. Suppose it is like this. So L you can define 2m e plus v0, right? H part. Okay, fine. So now if I consider for the bound state, so for the bound state, suppose E is actually negative, and so minus v0 is always less than E. Okay, if it is if though it is negative, if E is negative, suppose E is negative for the bound state, so it should be greater than minus v0. Okay, so this term is always positive. This term will give always positive. Because it is v0 is much lower and it is more lower, so okay. So this is positive. So the solution will be the periodic function. So if you write in a sine and cos term, sine lx, L here is plus b cos lx. Now one thing you have to know here, that if some potential is, suppose even potential and symmetric and even, then any one solution is actually you can consider either sin x or cos x, odd or even. So I mean both the solution actually allowed. So here we will consider just even part, and if you want you can calculate for the odd part also. So here I will consider just the even part. So the now psi will be, if I write in a compact form, minus kx. Okay. Oh, I have not still I have not find out this one, right? Okay, so okay, I'm writing all those things first. Let me define later. And okay, and on the first one, okay, and the exponential kx. Okay, so we have already calculated this one. Okay, this one is actually minus a, less than minus a, and this is for this part, and this is for x greater than a. So in a similar way you can find this one where we have found this part, this solution. So in a similar way you can find for x equals to greater than a, where actually potential is 0. So now so I will try to solve these coefficients and applying boundary conditions. So already you know the boundary conditions actually, that psi x is continuous at the boundaries. So first I will apply those conditions. So psi x is continuous at x equals to a. So x equals to a means these two equations. So f exponential minus ka equals to b cos la. And for d psi dx it will give minus k f exponential minus k a, and for minus l b sine, it will be sine la. Okay, so now limit 1 and 2. Oh, this is not visible, right? So this was not visible. Okay, now you can see. So it is for at x equals to a, it is continuous. I have applied that condition, and d psi dx it is also continuous at x equals to a. So it is continuous. Again, the video is it's problematic. So okay, so from this 1 and 2 equation, from 1 and 2 you can find k equals to l tan la. Okay, fine. Okay, nice. So now let me define la equals to z. Okay, and l equals to z, and also z0 equals to x dot 2 and v0. Let us define these two notation now. So and also you can easily find, see this one. Now suppose we are applying k square. K square. See here you have considered k. Okay, I am writing this one, k square. Okay, plus suppose l square. Okay, so from these two, l also you have defined, right? L find, where is l? L is there. Okay, so from these two you can easily find 2 and v0 by h part square. So you can see a similarity from here, why we have considered z equals to a and z0 equals to this. There is a relation with this one. So simply you can find out ka equals to z0 square minus z square. Okay, actually we are simplifying this equation to find actually z. What is z actually? La we want to find z actually. So we are forming some equation to solve z. So in this way, so if you put these values in the this equation, you can easily find like that equation, z0 by z square minus 1. in any book you can find this solution actually. So so it is actually easy to find out and easy to read the solution, but it is tricky to understand the results actually. Just you focus on how they solve this equation. This equation is called actually transcendental equation because where I mean in the both side you can see is a function of z, and we want to find the z value. So it is something like that. What we want to find is a function of that. I mean that parameter. So it is confusing. So this type of equation actually I mean solved using numerical method, and also in computational method one can solve this type of equation. So in computer it is better to solve. Already you have done multiple programs in Python. So you can easily fit this equation in Python by using matplotlib. You can see how one get the solutions. Yes, I will explain how we get the solution. So first, so this type of equation actually considering two equation actually. One is this function and another is this function. So this type of equation actually looks like that. In Griffith you can see these, and also in other books you can see. Okay, so this is. So in this way it will go on. So this is actually tan z, this also tan z, and here the function will go on. Okay, so suppose like this way. Okay, this is actually a function of z is 0 by z square minus 1. Okay, this is the function, and this intersection point are actually solution of this equation. So depending on the z value, here is the z value. So depending on the z values, this equation will be like that. So it can, the end actually depend on the z values. So as well as also the solution will be vary. So now in this equation, from this graph, one thing you have to understand that now see here that suppose let's see that two conditions actually. We will consider two conditions. One is actually if z0 is very large, and other one is if z0, if we decrease z0, so what will happen actually. Now so first consider case 1 when z0 is very large. Okay, so here you can see that here I have not written these values. These values are actually pi by 2, this is pi, this is 3 pi by 2. Okay, so in this way it will go on. So now you can see that always there is a solution or intersection just in front of the pi by 2 terms. Look at this. Here also there is a cross section here. It is just before the pi by 2, and here also I have not drawn the perfectly this picture. If you look at the Griffith book, you can see the picture correctly. So here is also the solution is just in front of 3 pi by 2, and also if I increase the z values, always the solution will be just before the something into pi by 2. And also it is something means n pi by 2. It is before just n pi by 2 if z is very large, and n have to be an odd number. Now you can see here is 1, 3 odd number, and also in next there will be 5, 7, 9. In this way, if you increase z0 in very large value, so you will get n in just above the just before that n pi by 2 value. Okay, so I can consider that value is actually n pi by 2. So Zn comes like n pi by 2. Okay, so n is odd. So now what will be the energy actually? If you put the z value there, you can find So we'll get this like of actually value, energy value. This is interesting actually. This is the something like solution what you will get in the infinite square well actually. But the width is defined here is 2a. If you solve infinite square well, if you can do it yourself, so you will find something energy like n square pi square h square by 2ma square. Here it is 2m 2a square. Okay, however, here is there is a bound value of n. So there is a boundary value of n. Above that you cannot go. But for the infinite square well, it is unbounded. You can get any number of energy states. But here it is bounded. So now we will consider when number 2 case z0 decreases. So if you decrease, now look at the picture. If you decrease z0, then so below pi by 2, you can see there is only one solution. You will get one solution. And interestingly, whatever value z0 can take, always you will get one solution. Now here you can see that tan z starting from the 0 position. So whatever can be the z value, it can be like this way, it can be like this way, whatever. Always you will get at least one solution, at least one energy state. Got my point? So that means, so always you will get at least one solution. So this is actually interesting, and you have to understand this thing carefully. Okay. This is the significance of this figure actually. So now we will move on to the scattering steps. So up to now we have discussed where energy is actually less than 0. Now we will consider energy is greater than 0. So energy is greater than 0. Okay. So as usual, here Vx equals to 0. From the definition you can get. So solving the equation easily you can form. Okay, let me write d square psi dx square equals to 0 into a. Okay, directly let me write it. Okay, k square psi, where k you are defining 2me by h cart. Okay, now this equation gives solution as a periodic function. So it is a very conventional solution. Ikx plus b exponential minus ikx. Okay. So it is okay. So so this is actually for the left side. That's okay. Now inside the well, Vx equals to, so inside the well, Vx equals to minus V0. So what we have got in the previous section, likewise we will get solution. I am writing this directly, okay? From the previous as it is in the previous section. So this is actually for minus a x a. Okay. So already you have defined this one. So h cart. Okay. So this was okay. And for the right section, and since it is a scattering states, so we have to consider only the wave towards the right. So for the x greater than a, you will get psi x exponential ikx. Okay. So because you have not considered minus exponential minus kx, because you are here considering the scattering states. So for the scattering states, we will consider only the wave moving towards right direction. So now you will apply boundary condition. So applying boundary condition, psi x is continuous at x equals to minus a. So you will get ika plus b exponential ika minus c sin ma plus b cos la, and also d psi x dx is continuous at x equals to minus a. Similarly, you will find a exponential minus I k minus b exponential I k l c la plus d sin la, and also at x equals to a, same applying the same boundary conditions, you will get c sin la plus d cos la f exponential I k a. Again for d psi dx, it is for psi x and it is for d psi dx. L c cos la minus d sin la I k a exponential I k a. Okay. So now solving those equations, you can get b equals to I sin 2la by 2kl l square minus k square f. Similarly, if you can do it at your home and you can check it out. Sin 2la. So here you can see from this term you can easily find out transmission coefficient. So it is 1 plus v0. So t is defined as, let me define it first, f square by a square. Okay, so you can find t inverse v0 square 4e plus v0 sin square 2a h cart root over 2n e plus v0. And this equation actually looks like in this way. It is the graphical representation. It is E, it is T, it is one line. So it looks like in this way. Okay, so this is the transmission coefficient now for 1. So if t equals to 1, so it is actually transparent. You can call that boundary is transparent, totally transparent, or you can it is the case of perfect transmission. So and also you can, if t equals to 1, you can find 2a h cart 2m e plus v0 equals to n pi. So from here you can calculate e plus v0 as n square pi square h cart square 2m to a square. So